Okay, hi. I'm Lisa Lippincott, and I'm here to talk about the truth of a procedure. But more generally, I'm here because I became interested in this question. Why don't we routinely write down the reasoning behind our programs in a formal way and have computers check our reasoning? You would think we would do this because we're really good at writing things down in a formal way. And we know what our reasoning is, so we ought to be able to write it down. And we're pretty good at writing computer programs that check things. This would be tremendously valuable. And yet, for the most part, we don't do this. And the best answer to this question that I've come up with is this. The mathematical tools we use for proofs present a poor user interface for programming, and in particular, for procedural programming. So we've got mathematical tools that work. The math is right. It's just really hard to use in the context where we want to use it. And I think by improving the mathematical tools, by improving the user interface for the math, we can make it possible to integrate checkable proofs into our programs. And that brings me to my home field of mathematics, which is logic. Logic is the part of mathematics that deals in what it means to write down something in a formal way, what it means for a sentence to be true or false, for one sentence to imply another, and for what it means to prove something. That's logic. And today, I'm going to be talking about what I call procedural logic. That is, logic that is expressed in a procedural way so that it fits into procedural programs. Logic that is about events in the world rather than about Platonic concepts. And the central metaphor in procedural logic is this. Procedures are sentences. That's fairly dense. So I will expand. By a procedure, I mean an embodied algorithm, a scheme by which events may be arranged in time, space, possibility, and causality. I mean what we mean in C++ by the word function. But I don't mean what mathematicians mean by the word function. I don't mean a mapping from input to output. A procedure may produce a mapping from input to output. But here I'm looking at procedure as an arrangement of events. I'm looking at it the way a procedural programmer has to look at a procedure. Sentences, on the other hand, I mean in the logical sense. A sentence is a statement about the world, which may either be in agreement with the world, that is to say, true, or in disagreement with the world, that is to say, false. And when you see this connection, you might wonder, what are our procedures saying about the world, and why would we care whether they say something that's true or false? Well, every procedure has within it a statement about the ways in which events may be arranged in its world. And of course, its world is the computer it's running on. Broadly speaking, it's the libraries it's running on, the operating system, the computer, the interaction with the user. It's all the things outside that the procedure is going to interact with. So its world is a computer in a broad sense. And the procedure says something about how events can be arranged. And if it's in agreement with the world, if it's in agreement with the computer, that's fine. But if it's in disagreement with the computer, if it's in disagreement with the world is going to win. And events will not be arranged the way the procedure suggests. The usual outcome in this case is undefined behavior. We leave this whole, if you can't arrange events the way the procedure suggests, then just have some other events happen. Do whatever you want. So a procedure that is in agreement with its world is one that can be implemented without undefined behavior. So to get a little deeper into that, let's look at sentences. This is an example of the sentence. It's not a sentence that says very much about the world, so don't worry too much about that, but it will serve as an example for us to start with. You might be used to thinking of a sentence like this as a tree, and there are a set of rules that you can apply that color in the nodes moving from leaves to root, letting us arrive at a color for the root node that tells us whether this sentence is true or false. And that's a fine, very algebraic way of looking at a sentence. But it's not the way I'm going to look at the sentence today. Today, I'm going to use a different formulation that's often favored by logicians. I'm going to turn the tree around like this, and I'm going to create a game that we play from the root of the tree towards the leaves. And this game has two players. Traditionally, they are named Player 1 and Player 2. I can never remember which one is Player 1 and Player 2, so I'm going to call them the bald guy and the guy with the horns. These players can see the game laid out in front of them. They know what's coming, apart from the other player's moves. And at each node, they're going to do something depending, the player whose turn it is going to do something. I've colored the nodes according to the turn of the player. So at this first OR node, the bald guy makes a choice of which way to go. At the AND nodes, the guy with the horns makes a choice of which way to go. Now I've colored the node labeled true for the guy with the horns, which you might think is odd because that's the symbol usually reserved for the Prince of Lies. But this is because this is the sort of game you can only lose on your turn. When it's not your turn, you're safe. So each player is working to end their turn, turn it over to the other player so that the other player might lose. And they can't do that at these true and false nodes. So at the true node, it's the turn of the guy with the horns, and he loses, he's unhappy about that. At a false node, it's the turn of the bald guy loses, he's unhappy. So that's how we play this game. And either player could win this game. There's a way it could go for each one. But one of them has a winning strategy. There's one player who can throw away some of his moves, leaving a game where he cannot possibly lose. In this game, it's the bald guy. He can throw away some of his moves. He's in a game where he is certain to win now. And that means that this sentence is true. True is the bald guy having a winning strategy. You might be wondering, well, this is all very well for and and or, true and false, but what happened to not? Not makes sense in the algebraic version. It's a node that inverts the color. We can write a gate for that. But there's no not in this tree. And not is something a little different than it is in the algebraic version. Not is exchanging the roles of the two players. So if we flip every node over to the other player, we get the negation of the sentence. And if one player has a winning strategy for a sentence, the other player will have a winning strategy for the negation of the sentence. And the strategies are going to have the same shape, like this. So that's enough about sentences and games. What we're going to do is we're going to play a game on our program, on our procedure that we're interested in, and see who wins. First, a warning. The code here is written in a fantasy C++ with extensions that make the proofs fit into the code. Unless somebody's gotten way ahead of me, this will not work on your compiler at home. So here is our playing field. This is a function, foo, in the center of the screen. That's center court for our playing field. And the edges of the court are the interface to foo and the interfaces to the functions that are called from foo and from its interface. So play in this style of interface runs like this. We start coming in through the interface of foo, running its prologue, which explains conditions that have to be met before we enter the implementation. You may be used to this pattern from virtual function. This is the pattern for putting an interface on a virtual function. I'm extending it here to put interfaces on arbitrary functions. So we come in through the prologue. Once we've executed the prologue, we enter the implementation. And we execute the implementation. If we make a call from the implementation, we go out to that function through its interface, through its prologue, out to its implementation, and back onto the field through its epilogue. If we reach the end of our implementation, we exit through the epilogue, which explains the conditions that must hold at the end of the function. And we're going to divide this game up into turns, like this. The guy with the horns starts the game. He brings us onto center court through the prologue. But as soon as we reach center court, the bald guy takes over. The bald guy plays everything that's in center court. And if he makes a call outward to this function bar, he plays the prologue until play goes off the court. Play is returned to the court by the guy with the horns, who plays the epilogue. When we reach center court, bald guy takes over. If the bald guy manages to knock play off the court through the original interface, go out through the epilogue, and the guy with the horns has a turn he's not happy about. So that's how we divide it into turns. But it's best to think of this not as a sequence of turns, but rather as a set of nested turns. So there is a single outer turn for the guy with the horns, representing the stuff that happens when our function isn't running. And there's a turn that represents the execution of this function foo that the bald guy plays. And then there are a lot of little turns that represent returning the execution of other functions and returning to center court. And that's played by the guy with the horns. So our turns are nested 3 deep. And that lets us define a rule for what happens if the game goes on forever. If we get stuck in the epilogue of a called function and the game goes on forever, we call a delay of game penalty against the guy with the horns. He loses, the bald guy wins. If we get stuck in the implementation, the bald guy gets the delay of game penalty. He loses, the guy with horns wins. Even if we get stuck in the implementation constantly calling out to other functions here, the guy with the horns in this case ended all of his turns, whereas the bald guy had one big turn that went on forever. So the bald guy loses in this case. And of course, if we get stuck in the prologue, that's the fault of the guy with the horns. So that's how delay of game penalties are assessed. For the rest of the gameplay, I'm going to switch to a particular function so we can actually follow the execution. And this is the interface for the function I've chosen, the traditional factorial example. Here, there's a bunch of new stuff in this interface, so I will explain. A claim statement is a kind of assertion, but it's a special kind of assertion. It's one that must hold for local reasons. The reason isn't allowed to just be in your head. It's not allowed to be in some other program or even far away in this program. It has to be somewhere close to the claim so that we can see that relationship. But it also has to be somewhere before the claim. So in this case, the purple claims are happening for reasons in other functions. If one of those claims fails, it's not the fault of our function. Whereas the yellow claims, down at the bottom, if they fail, it's the fault of our function. And we're going to assess a penalty. If a claim fails, the current player loses. And I think that's enough about claims. But there's also this thing, usable. Usable is a weird kind of assertion. It's an assertion about an L value. You might not be used to those. We're used to assertions about R values because we get all of this precondition, postcondition stuff from functional programming. And it gets a little more complicated in procedural programming. We have to talk about the ways in which things are going to be used and changed. And here, the usable is a very object-oriented kind of assertion. It depends on the type of the thing you're using. But for scalar values, which we're going to be seeing today, a scalar L value has a stable value if it's not volatile, and it's modifiable if it's not const. There are a few other things involved in being a usable int. You can bitewise copy it or one or two other weird things. But really, this is the core. We have a stable value for n when we assert that n is usable. Class types might have more complicated rules for usability. If you look at what usability is for a vector, well, there's a whole range of usable elements, and you need to be able to loop from one end of that range to the other. And if it's non-const, then it might be relocatable. Usable gets complicated for class types, but we're used to things getting more complicated and specialized for class types. So let's begin. First thing that happens is we leave this interface because we hit this greater than or equal. That's a function call, built-in operation, but we're going to treat it as a function call. So we have to look at the interface for greater than or equal, first thing. Let's play through. Here's the interface for greater than or equal. As we play through these claims of usability, because the variables are not volatile, we're going to call out their values. So the value of A is 6, and the value of B is 0. Guy with the horns is playing at the moment, so he calls out the values. Why do we call out the values? Well, it helps the judges know what's going on, and it entertains the spectators. On our way out, we call out some more values. But there's a rule here that because we didn't say A or B could change, because they're const, the guy with the horns has to announce the same values he announced before. So A is still 6, B is still 0. He gets a bit more freedom with the result. And now we can continue back to our interface. And as we come through here, we see there's another claim of usability. Now, we've claimed the usability 3 times already. You might be wondering, why are we so repetitive? Well, before, we claimed the usability with respect to greater than or equal. Here, what we're saying is that the value of n is going to be important not just to greater than or equal, but also to the factorial function. The value of n is part of the direct input to the factorial function. Now, you know, if there's direct input, there must be a kind of indirect input. What's the indirect input here? It's the address of n. It's whether the bytes of n are stored in a cache or maybe in main memory. Where in main memory is it? Is it on a disk? Do you need a credential to get to it? Do you need some sort of encryption key to find out the value? All of that stuff, indirect information, indirect input for the procedure. We can't run the procedure without it. But it's not the important stuff. It's not the stuff that the procedure cares about. But on a modern architecture, an int has way more indirect input than it comes as more indirect information than direct information. Moving on, we can run into our implementation. And I've tried to write a careful implementation of this function. I'm being careful about overflow. Not the most efficient, but I think a good teaching function anyway. This is, I'll give you a minute to read it. This is a fairly simple function. Dense in that C++ way. And that density is going to cause me a little trouble when moving around it, so I'm going to explode it. This is a diagram of the function. We're going to start by initializing a couple of integers. We're going to have a loop where we do our multiplication. There are two ways out of the loop. We can get out when we reach 0, or we can get out when we find some numbers that don't multiply together. Let's begin. We initialize an integer. There must be an interface for that, a constructor-like interface. Usability on the way in, call out the value. On the way out, there is this unusual claim, substitutability. This is the dumbed-down version of equal, or it's the procedural programming version of entanglement. It's the same value being correlated in two different locations. We bring them together and compare and say, oh, look, they're substitutable for each other. So substitutable, the current player is going to lose if there are two different values. Other than that, fairly straightforward. Two claims of usable on the way out. You will notice that star this is not const, and so the guy with the horns mentions that it can be changed. Back to our implementation. There's another initialization that's boring now. So we will move on to this test. I not equal to 0. We are off to operator bang equals, which immediately sends us somewhere else. I've chosen to write this one as an inline function because it is actually much easier to write that than to write a careful interface for what bang equals does and relate it to how equals works. And people do ask me, why don't you just do that all the time? Why don't you just examine the code and say it does whatever the implementations do and work out the reasoning of the whole program from that instead of writing these complicated interfaces? And the answer to that is, well, it doesn't scale well. Looking at the whole program is hard. Looking at one procedure and the interfaces that it touches is much easier. But also, doing that makes your program reasoning brittle. Here, I'm tying the definition of not equal, equal, and not together in a tightly coupled way. And in this second function, I'm tying not to true and false in a tightly coupled way. And if anything changes about those relationships, it's going to break all the code that sees these functions. Now, as a member of the C++ committee, I think that we are committed to preserving the particular relationship between not equal, equal, not, and true and false for many years into the future. So I feel pretty confident in this case writing these as inline functions. But if you don't feel confident that those relationships are going to last forever, maybe you want to write an interface and give your code some room to slide around. Okay, off to equal. Here, same thing coming in, 2 usable values. We have a branch in the output. The result is false, so we're avoiding that claim of substitutability. I'm going to say the branch directions that we take are part of the direct input and output. And that's very helpful because it means if you know the direct input, you know every claim that was made on the way into the function. If you know the direct output, you know what claims were made on the way out of the function, and that's going to help our reasoning. And coming back, the bald guy plays through all of this code. It's not terribly interesting. And we're back to our implementation. We hit CanMultiply, off to another function. This one's pretty boring. CanMultiply just tests to see whether the numbers are small enough to multiply together. And if they are, it says yes, and if they're not, it says no. It has what I call a basic interface. And this is an opportunity to plug another lecture of mine. You can go online and listen to me talk about the basic interface in a talk called What is the Basic Interface? Comes in 2 versions. There's the BoostCon version, where the audience asked lots of great questions. And there's the CPPCon version, where the videographer lasted to the end of the session. So you have that choice to make. But otherwise, this is a fairly boring function, and we're ready to multiply. Or we would be ready to multiply if the first thing in operator star equal wasn't a claim of CanMultiply. Of course it's a claim of CanMultiply. It's the precondition, a precondition for operator star equals. So back to CanMultiply. We play through again, and this is where we use that idea of direct input and direct output. We are repeating the direct input that we used before. And so the guy with the horns is required to repeat the direct output. That does say something about how we should write our interfaces. If you're returning an error code or something that's not repeatable, then you want to make sure that it's not direct output. Treat that as indirect output. And that's just a way to write things. It doesn't, it's not very hard to control which things are direct and which things are indirect. Okay, so we come through, we get the same answer as before, which means this claim is going to succeed. And we've got one more weird thing to claim on the way out. We have this claim of aliasing. Result and this refer to the same object. And I'm not going to go into it deeply today, but we do need a rule that says there's a penalty for not mentioning aliasing as you go through an interface if that aliasing, if that causal connection can be observed by the other player. So here, the guy with the horns was required to mention the aliasing. It would have been a penalty if he hadn't. But because there was a claim of aliasing, he did mention it, and it's fine. And that way, the judges and the spectators know which L values refer to the same object all the time, because all the aliasing that happens that matters is mentioned in the interfaces. Okay, we can move on. We have multiplied. Are we done yet? No, there's one more operation. We have to decrement this variable I. I'll run through that quickly. Decrement has a precondition, CanDecrement. CanDecrement is a Boolean function with a basic interface. We come back, there's a postcondition of CanIncrement, because anything you get out of decrement, you can increment. And there's also a postcondition mentioning the aliasing, because we have this weird interface where star this and the result refer to the same object. And a bit of usability. These things can change because they're non-const, and we're done. And now we can just repeat that a few times around the loop and eventually head out to our return statement. Are we done yet? No. We'll put this back together and head for the epilogue. But the epilogue is fairly simple. Bald guy announces n still 6 because it wasn't changeable. And the result here is 720. So is that our game? No. One more turn. Little surprise for you. The guy with the horns is allowed to call for a rematch. Your function can get called more than once. And if he does, he has to follow that same rule from before, or the bald guy has to follow the same rule from before. If the direct input is repeated, the bald guy is required to repeat the direct output. And that goes on possibly forever, but if it goes on forever, there's a delay of game penalty, guy with the horns loses. That's our game. And in this game, you will notice that the guy with the horns announced all the input, and the bald guy announced all the output. And I mean this in a very broad sense. You don't usually think of multiplication as an input-output operation, but procedurally it is. We output parameters to the multiplier, and we input the product from the multiplier. It's something that's happening outside our procedure. So here we have output and input broadly construed, not just the direct input and output, the gross input and output. And we had 5 penalties as we went through. You can get a penalty for getting stuck in a loop. That's the delay of game penalty. You can have a penalty for an assertion failure. You can have a penalty for unexpectedly announcing a different value when you should have announced the same value. You can have a penalty for inconsistent function results. The direct input didn't match or the direct output didn't match even though the direct input did. And we have that weird penalty for not mentioning the aliasing when the judges and the other player needed to know about it. And when we're done, we see that the bald guy wins the game of truth if the first penalty goes to the guy with the horns, or if there's no penalty at all, if the guy with the horns just gives up after a while. The guy with the horns wins if the first penalty goes to the bald guy. And that means that the bald guy has a winning strategy if the first penalty goes to the guy with the horns for all input values. Whereas the guy with the horns has a winning strategy if the first penalty goes to the bald guy for any input value. There's that asymmetry, this different quantification for all input values for some input value. And that asymmetry comes from the directional asymmetry going in and out. The guy with the horns is the one choosing all of the input. So just one input that makes the program go wrong lets him win, or lets him have a winning strategy. His strategy is choose the input that makes the program go wrong. We could reverse that, saying something about the output. It becomes maybe a less interesting statement. On the other hand, every exit is an entrance somewhere else, so that says something about the outside world. The procedure is true if the bald guy has a winning strategy, just like I promised. The procedure is false if the guy with the horns has a winning strategy. Back to the title of the presentation. You might wonder, this is a much more complicated game than the one I showed you before with the ands and ors. Is it necessary that one of them has a winning strategy? Could there be a game where neither player has a winning strategy? Could your procedure be neither true nor false? And we do have an answer for this. These games have a topological property. They're Borel games, named for Émile Borel, one of the founders of game theory. And in a Borel game, if one player doesn't have a winning strategy, the other player certainly does. That wasn't proved by Borel, that was proved by Donald Martin back in 1975, his theorem and his paper called Borel determinacy. This is one of the really important theorems in logic. Now, a theorem like this can lead you to look at the world of sentences as being neatly divided. We can dividing line down the middle, there's the true sentences on one side, the false sentences on the other side. And this is a good way to look at some areas of mathematics. Euclidean geometry, one line, true on one side, false on the other. Algebraically closed fields of any characteristic, true, false, that's all there is to know. Dense linear orderings, that is, total orderings where there's always something in between. Once you know whether you have endpoints on it, there's a neat line between the true and the false. But these parenthetical remarks here, the characteristic of an algebraically closed field, that's basically knowing what uint max is. It tells you at what point your arithmetic wraps around. And depending on what uint max is, different things are going to be true. Dense linear orderings might have a first point, they might have a last point. Might have both, might have neither. And certain sentences, like the sentence, there is a first point. True for some dense linear orderings, false for others. In order to get this nice line between true and false, you have to know the parameters of the situation. That is, dense linear orderings really look more like this. There are 4 kinds of dense linear orderings with different lines between the true and the false. And we know what that is from an engineering point of view. This is implementation dependence. And we have a couple of ways to deal with implementation dependence. If it's implementation defined, we look it up in the documentation. We can find out what our implementation does, and that will tell us which procedures are going to be true and which procedures are going to be false. And that works pretty well for dense linear orderings, but sometimes it's a pain to look things up in the documentation. So instead, we write portable programs. And when we write portable programs, we form all the possible computers into an ensemble. And once we have formed an ensemble, we see that, broadly speaking, there are 3 zones that we can worry about. The ensemble divides sentences into the necessary, the merely possible, and the impossible. That is, there's things that are necessary are true no matter what computer you're running on. Things that are merely possible are true on some computers and not on others. And the impossible is the things that are not true on any computer. So once we form an ensemble, things are divided 3 ways. And we're kind of stuck with this for programming, because those undecidable halting problem programs you've heard about, those are in the possible. They're true for some computers, they're false for other computers. And what's more, there isn't documentation that's going to tell us which computers they're true for and which computers they're false for. We don't make that implementation defined because that would require the implementers to write an infinite amount of documentation. And they don't like writing an infinite amount of documentation because they figure no one would read it anyway. So instead, these undecidable halting problem programs will work on some computers and not on others. And we have no way of knowing which kind we're running on. So we avoid those. As engineers, we know that the good programs are necessary. They're going to run portably. Whereas programs that are merely possible, the undecidable ones, they're bad programs. And of course, the impossible ones are also bad programs. We try to write the ones on the left, the necessary programs. So how are we going to distinguish this? We'll play a game. We're going to modify our game so that the bald guy only wins in the necessary, whereas the guy with the horns wins in the possible and impossible. And to do that, we're going to have to give the guy with the horns some kind of advantage. So here's the question. Is there some advantage we can give to the guy with the horns so that the bald guy wins only if the procedure is necessary? And yes, there is. We can put the guy with the horns in charge of the computer. And by the computer, I mean, broadly speaking, the computer. The libraries we call the operating system, the hardware, the user interaction, everything outside of our procedure, we're going to put the guy with the horns in charge of. This is going to make the game much harder for the bald guy. So instead of running through the whole program, I'll just detail the changes. First off, instead of choosing values when we come to a claim of usability, the guy with the horns names the values. It says, that one is Sue, that one is Zachary. Very easy for the guy with the horns to do this. But we still have the rule, when the value hasn't changed, the guy with the horns has to use the old name so that we know he's referring to the same value. So here we have Sue and Zachary again, and the result here is Bob the Boolean. Now, that's going to cause us a problem when we come to a branch, because we don't know which way Bob the Boolean goes. What happens when we come to a Boolean claim or a branch? The guy with the horns chooses which way that sort of Boolean goes. Here, Bob is a left-turning Boolean, so the claim succeeds. And we do have a rule. The guy with the horns has to be consistent about this. If Bob turns left once, Bob turns left at every branch. If Bob turns right once, Bob turns right at every branch. So this is an extra penalty for the guy with the horns. And finally, if we come to a claim of substitutability here, then the guy with the horns just comes up with some excuse for the two names to refer to the same value. Claims of substitutability are very easy for the guy with the horns. There is a way it can go wrong, though. If you have two Boolean values, one that's left-turning and one that's right-turning, the guy with the horns can't say they're the same because a left-turning Boolean has to always turn left and a right-turning Boolean has to always turn right. So things are much easier for the guy with the horns in this game, and we're going to make things correspondingly harder for the bald guy. Instead of announcing values, the bald guy has to repeat a name already introduced by the guy with the horns. And that's fine if the guy with the horns has already given the value a name, but if there isn't already a name, the bald guy is stuck, and he loses. If we come to a branch, bald guy doesn't get to choose. He has to ask the guy with horns which way things go. So branches are always the domain of the guy with the horns. Bald guy has no freedom about them. And of course, if that branch is in a Boolean claim, and we haven't already established that that Boolean is going to turn left, then the guy with the horns has an easy way out. He can just call it right and end the game right there. And finally, when we come to substitutability, the bald guy has to repeat whatever lousy reason the guy with the horns gave for the two names referring to the same value. And if he doesn't have a reason, if those names haven't already been explained to refer to the same value, he's going to lose. So everything's easier for the guy with the horns, everything's harder for the bald guy. But what this amounts to is, in this game of necessity, the guy with the horns is telling a story about the world, about the computer we're running on. And the bald guy is explaining how the procedure executes within the story. The bald guy doesn't get to invent anything new because he has to stick to the story that the guy with the horns is telling. There are 7 penalties here. Analogues of the original 5 on the left: stuck in a loop, assertion failure, unexpected name change, because we're not talking about values anymore, inconsistent result names, unmentioned aliasing, still a problem. But there's a new penalty for the guy with the horns if he has inconsistent branching. And there's a new penalty for the bald guy: any claim that is novel, that hasn't been made before, that comes up on the bald guy's turn. If he can't break it down into parts, he's just going to lose. And when we put it all together, we get this theorem. The bald guy has a winning strategy for the game of necessity if the procedure is true for all possible computers. So that's what we were looking for. And that's a fairly easy thing. If you can win in a story, the real world is like a story, so it's going to work in the story of that computer. The other side is a little more complicated. But the guy with the horns has a winning strategy if the procedure is false for some possible computer. And to prove that, we actually need a technique for figuring out how possible computers execute. And Paul Cohen, back in the 60s, came up with this neat technique called forcing. Forcing lets us find possibilities that are on the edge of necessity. And in this case, it lets us find possible execution paths that aren't necessary execution paths. That is, execution paths that some computers can follow and some can't. So forcing, clever math technique, gets us this theorem. This is also, by the way, the technique. In fact, it was introduced in when Paul Cohen proved the independence of the continuum hypothesis and the axiom of choice. So some big famous theorems there. Now, what happens if we play the game of necessity on our program? You might have seen it coming. We had one novel claim there, which is that the numbers are going to be decrementable. The bald guy is the first player to claim decrementable. Now, we know this shouldn't happen. There is something wrong with the story that the guy with the horns is telling about the computer. if this can happen. There ought to be a rule against that. So we're going to come up with a way to introduce rules about the sorts of stories that the guy with the horns is allowed to tell. For that, we're going to have to give the bald guy an advantage. And the question is there some advantage we can give to the bald guy that's stronger, that stands up to putting the guy with the horns in charge of the entire world? And it turns out there is. If you can't change the world, you can change the game. We're going to team up with the bald guy to write the procedure. We're going to intentionally write procedures that are necessary rather than just running whatever procedure we picked up in the gutter that day. And in this game, there's really just one new rule, and it's a rule just for the bald guy. The bald guy gets to insert claim statements into the implementation as we play. And we're going to let him claim special functions. I will call them theorems because we don't have a great name for them in C++ yet, that express rules about what the story can look like. So here's an example. This countdown theorem expresses the relationship between greater than or equal and the ability to count downward. So in this case, we can count down from high to low whenever high is greater than or equal to low. So this is a function that doesn't change the execution path. It doesn't modify any of the data. It's just something we can assert as we go by. And the effect is that the bald guy gets to ask a question. How do you count down from Sue to Zachary? And happily, the bald guy has summed up what goes on in greater than or equal, so we don't have to show that. But the bald guy is responsible for getting us through the prologue. He has to win at this claim of greater than or equal. But if he does, it forces the guy with the horns to explain how you count down. Because as the guy with the horns walks us through this loop, he's going to have to show how long it takes to get from Sue to Zachary. And it's going to be a finite amount, or else he gets stuck. And as he goes, he's going to have to show us that Sue, Frank, Faye, Ted, Terry, and Ollie are decrementable. So all the stuff we need in order to do the counting down, he has to do because he's doing the counting down. So in the game of proof, the guy with the horns is still telling a story, but the bald guy gets to ask questions, forcing the guy with the horns to expand on the story and make it follow the rules. And once again, we get a result. Here, if the bald guy has a winning strategy for the game of proof, the procedure can be made necessary by adding claims to the implementation. That is, if the procedure works on everything, and if the guy with the horns has a winning strategy for the game of proof, then if the procedure is false for some possible computer that obeys the rules. So these are both a little mathematically compact. The one on the left, or a little complex mathematically. The one on the left uses a property called compactness, a bit of topology there. The one on the right, you've got forcing like before. It's a fancy coherent laser forcing with filtered colimits. And it ends up with a finite injury argument I'll just say that mathematical logic is surprisingly violent sometimes. But the upshot of this is that either there is some possible computer that obeys all the rules that breaks your procedure, or there is some way to write claims into your procedure that make it necessary, that is, that make it a proof. So if the procedure works on all computers that obey the rules, there is a proof out there. All you have to do is cite the rules that you need. And that's a very hopeful result. It means that we do have a way of doing this. And mathematicians have been knowing this for a long time, because really this is some fancy new math. But it's pretty much an old theorem. This is Kurt Gödel's completeness theorem that he proved in his doctoral dissertation. It's the one nobody ever hears about. It wasn't much of a surprise at the time. Everybody expected this to be true, because nobody knew about the incompleteness theorems that Gödel was going to prove later. These days, knowing about the incompleteness theorems, this looks more surprising. You think incompleteness means there must be a hard part somewhere that maybe some of you know where it is, and maybe some of you are missing the hard part. The hard part, recursion theoretically speaking, is finding the proof. On the left, it just says the proof is out there. It doesn't tell you how to find the proof. And there isn't an algorithm for finding the proof. Recursion theoretically, this is hard. On the other hand, it's not so hard as an engineering problem, because we know where to look for the proof. If you ever go looking for the proof for your procedure, you don't have to look any further than right inside your head. Because if it isn't there, you never should have written the procedure in the first place. All you have to do is figure out why you thought that procedure should work and write it down. What rules about the computer you were relying on, write those into your program. Now, I do want to return to our program and say, this program got complicated because I chose that particular precondition. This precondition isn't the precondition that the function I wrote actually used. I said n was greater than or equal to 0, but what I used was the ability to count down from n to 0. And I had to cover that gap, that logical gap, with a theorem. But if I had simply written that n is the sort of number that lets you count down to 0, I wouldn't have had to call a theorem at all. This would have been a simpler interface in a certain way. There's something nice about this interface, which is by putting the loop in the interface, I'm indicating that this is a procedure that's going to count down. I'm telling you how complex this procedure is. So maybe I should have written that interface in the first place. Now, before I end, I want to return to this picture, because this picture is really the heart of the matter. This point where we divide the world up into yellow and purple. This is quantification, a bitopological separation into an existential part and a universal part, where we set the guy with the horns against the bald guy, our procedure against the world. This separation where we look just inside our procedure and treat the outside as trying to trip us up, is what is the core of logic. It lets us reason locally. But it's not the big picture. The big picture for our program doesn't have any demons. There are no demons. There are just a lot of bald guys out there, all trying to win their own games. And if we write our programs carefully, we can let every bald guy win their game of necessity. And on that note, thank you for listening. Are there any questions?
Hello. Thank you for the talk. So it's really interesting. But I believe that the way it was explained, it requires that you actually have a full view of the entire program in a way, where you can see all the claims for each of the procedures you are using and all that. And this is not always the case. And at some point, you need a way to bubble up, maybe in a upper interface, different claims, right? Only
no.
the interface is visible to other people.
So, okay, I didn't mention it here, but no, that's not true. You only have to see the interfaces of the functions that your procedure interacts with, and of your procedure itself. Now, you do need a way to make those visible, and that's why I use a separate declaration for the interfaces than for the implementations. The point is you put the interfaces in your .h files so that every neighborhood, every check of a procedure can be executed, it can be looked at within the translation unit of that procedure. If you want to see more on that, the basic interfaces talk goes into that in more detail.
Okay, but you could still have like a higher order function which has constraints on it based on the function which is passed in as a parameter.
By a higher order function, you mean a template?
Could be a template, could be.
If it has, yeah. So if you're talking about a template, then even in the instantiation of the template, at the point of instantiation, all of the interfaces you call need to be in scope. Point of instantiation, complicated rules, but that's C++ trouble.
Okay.
Hi, thank you for the talk. It was very colorful, surprisingly. I would be interested if, so if you go to this kind of lot of work to write down interfaces and the claims and everything, whether there is actually, or there are algorithms to disprove a procedure. So in a way, like this process that you mentioned on the right side, I can't remember what it was called. So if there's any way of automatically finding a counterexample, essentially, for a computer that will, where the procedure will fail.
So not exactly that, but something kind of close. So there is no algorithm that automates either of the players here. You can't automate the bald guy, you can't automate the guy with the horns, although you can approximate them. But what there is, you can automate the judges for the game. There are algorithms that check the proof. They don't find the proof for you, but they tell you whether you've written it. They tell you whether you have written down something that is a proof. So you can actually check the proof that you've written programmatically. And really that means we have to write more, but we should know what the proof is. All we have to do is write it down so it can be checked.
Okay, thank you.
Hello, thank you. Very insightful. There's one thing that I didn't grasp. Maybe it's because of the combination of game theory and the code. There was this substitutable in the operator, a comparison operator, where you only say something about being substitutable when the comparison is true, but you don't do it when the comparison is false. Is that somehow covered by the game theory?
A little bit. Substitutable turns out to be one of these weird things that substitutable lets you do things. There are functions that you can only call, things that you can only do when there's substitutability. But non-substitutability isn't a thing. That is, there is no function that requires non-substitutability. Sometimes we require not equal. That's a Boolean condition, you can negate it. But non-substitutability is something you want to avoid. And so in this logic, substitutability is something you can claim, you just can't put an exclamation point in front of it.
Okay, thank you.
Hi, thanks for, it was a very nice talk. I liked the humor in it, the bold guy and the, yeah. I was wondering, you already said there is some way to automate part of the checking, but when you try to kind of explain to colleagues why you think a procedure is going to work, often there is a big mismatch in what you think and they think is true. And it takes an enormous amount of work to synchronize that mismatch, to work it away. So I'm wondering, do you have an idea on whether it's, I don't know, time to start working on a common vocabulary on these kind of things, or common set of knowledge?
So I think it is past time to start working on that. That's why I'm here. I mean, it is true that, it's also true that when I try to explain to a colleague how a program is going to work, there's some slippage in the English descriptions, and I'm not always clear to my colleagues. But we're actually really good about being clear when we talk to the computers. We write things formally, and yes, there's a process of iteration of making mistakes and correcting them. But in the end, we end up pretty much agreeing with the computer on how our code is going to execute. Or at least we hope we do. The same thing can be true here, that once we get used to a language like this, I hope we can make it practical to learn to agree with the computer on what the reasoning behind the program is.
Okay, thanks.
Yeah, thanks for the talk. I really enjoyed it. It's become clear to me that I really shouldn't have written any of the software that I've written so far. Maybe I should shave my head and then I'll win.
If it ran, you probably did have reasons in your head why it would run.
My question is, trying to actually take this sort of advice and change the way I implement things. I'm having trouble picturing how I should change my code around things like function pointers, where is like the prologue and epilogue on the other end of the pointer? Do I need to make a wrap around the pointer at the call site to do that?
So,
how should I think about that?
Okay, so function pointers, bit of a step for C++ because you want the interface that you're calling the function pointer through to be part of the type of the function pointer. So we can approximate this with a wrapper class. That is, we have a class that contains a function pointer, it has an interface that asserts preconditions in the prologue, calls the function, asserts postconditions in the epilogue. So using that, you have an interface enforced on function pointers that fit into classes of that type. But what we don't have is a great way to go from the raw function pointer to function pointer with that particular interface that has any sort of enforcement right now. So you wouldn't want to make the constructor for that implicit. It's not you shouldn't make it a free conversion. Possibly you don't want to have a public constructor at all, but just a function that creates typed function pointer, that blesses typed function pointers out of raw function pointers.
Okay, thanks.
Thank you very much for your talk. I really enjoyed it, and I just wonder, where can I read more?
Read more is a little bit of a problem because I don't write all that much. I do have several talks online. I mentioned what is the basic interface. I did a talk last year, Locally Atomic Capabilities and How to Count Them, which is about how necessity turns these capabilities, these things you can assert but are defined elsewhere, into things that are conserved like atoms. That one you might find interesting. But if you look up my name online, there's a bunch of talks.
Thank you.
Anyone else? Well, thank you again.